Principles of Operating Systems. Chapter 4, Concurrent Processes, Synchronization, Deadlocks, Starvation. Again, consider two processes, producer and consumer, that access the same buffer. Producer produces values, stores them in buff. Consumer reads the values from buff, does something with them. Consumer should never try to read a value from buff until there's something there that producer has placed, and producer should never try to store a new value in buff until consumer has used the previous value. We are going to use two semaphores in this example. Writer, which the initial program initializes to 1, and reader initialized to 0. We can deal with this situation with the following combination of procedures. Producer, with a parameter, first executes P of writer. When P succeeds, the parameter is stored in the buffer, and consumer is initiated. Next, executes V of reader. When the consumer executes, it executes P of reader, does whatever it is that the consumer will do to some values in buffer, then executes V for writer. With this preceding pair of procedures, when some external process creates a value for our parameter and initiates an instance of producer with this value of the parameter, the semaphore procedure P clears the value in semaphore value writer to 0. So any new instances of producer will be blocked when it attempts to execute the first command P, and it'll remain blocked until something executes V of writer to increment writer again. Next command in producer is store the parameter in the buffer. Then it initiates an instance of consumer. The first thing that happens in consumer is P of reader. Reader is initialized to 0, so consumer cannot proceed until something executes V of reader. Well, that's the next thing that producer does, executes V of reader, and then the instance of producer terminates. So V executes and consumer can begin. This prevents consumer from trying to read something until producer has put a value in the buffer. only after producer executes buffer assigned parameter value and v reader. Now, any attempts by any processes to execute a new instance of producer are still going to be blocked because the semaphore writer is still clear to 0. And it's going to stay 0 and continue being blocked until consumer has processed the value in buffer, at which point it executes v of writer, increments the semaphore writer, and allows any instances of producer to proceed. So p writer executed by producer, followed by eventually consumer v of writer, creates a critical region. After p of writer and until v of writer, no new instance of producer can proceed. Similarly, we have another critical region, p of reader executed by consumer, until v of reader executed by producer, no new instance of consumer can proceed. So only one instance of consumer can be accessing the buffer at any one time. Now we want to consider a more complicated system. Instead of just one buffer, we're going to work with a system that has a number of resources that can be assigned to processes and deallocated as process finishes with them. Example, memory pages in a paging memory system assigned to various processes as they need them. This might very well involve multiple processes. In a multi-programming system, each process might be allocated several different resources at different times. Now, in this kind of a situation, we can represent our resources with entries in an array, a resource array. Each entry in the resource array, of course, is associated with a specific resource. And the values in these entries would also have a field identifying the process to which the resource is allocated. They're all initially set to null because initially they're not allocated to any process. Our system is going to use three semaphores, 2 counting semaphores and 1 binary semaphore. The counting semaphores named allocated and available. Allocated initialized at 0, available initialized to the number of entries in the array, and of course that's the same as the number of resources in the system, since each resource is identified with an entry, and each entry is identified with a resource. The binary semaphore will be named mutex, initialized to 1. Mutex is a name that's traditionally assigned to a semaphore used for mutual exclusion. In this example, we're going to make use of a function, assign, and a procedure, release. Assign has a parameter, process ID. It starts with P, available, then P mutex. I assign 0, and while resource array I of process is null, as entry number I is not null, it's assigned to something, I++, move on to the next one. When we get to a resource which is not assigned, then assign the parameter value, process ID, to that entry process field, return the resource number, identify the resource that's been assigned, and v mutex. And that terminates the activity for the function. Release procedure also has a parameter, resource ID. Start P mutex. I assign 0, while resource ID, resource array of I, resource is not resource ID, move on to the next. We search through the array until we find an entry whose resource value matches the parameter. When we found it, entry number I is that resource. We set that to null, making it once again available. V mutex, exiting the critical region, and V available, incrementing the number of resources now available. And that terminates the description for the procedure release. With this construct, any number of processes can attempt to execute assign, create instances of the function assign. Each attempt starts with P available. If semaphore available is 0, the instance is blocked and the process is placed in the available queue of blocked processes. Now, the way we have it set up to max processes can succeed in executing P available. And the next step is to attempt P mutex. Mutex was initialized with 1, so the first process instance executing P mutex sets the semaphore value to 0 and proceeds. All subsequent attempts get placed in the mutex waiting list. No further instance of assign can execute P mutex until there has been executed a V mutex. Neither can release execute P mutex until the first instance of assign has found a resource, allocated it to the process, and then executes V mutex. When assign executes V mutex, it returns the semaphore value mutex to 1, and if there are any blocked processes in the mutex waiting list, releases 1, so that it can go on to attempt P mutex again. And if it succeeds, proceed in execution. Any process, after being assigned a resource, when it's done with it, it can release that by executing release, identifying the resource to be released. This results in making that resource available for reassignment. It sets the process field in the corresponding resource array entry to null, so that it can then, so that it can be reassigned. And then it increases the count of available resources by executing V available. A deadlock occurs when several processes have resources assigned, but none of them can proceed because they need other resources, but the other resources can't be assigned because they've already been assigned to other processes which cannot proceed because they need resources, and so on. The way to avoid deadlocks, the only sure way to avoid deadlocks, is to require that every process identify all the resources it's going to need before it's allowed to start. So that any process that requires a resource already committed would have to wait until that and any other resources that it needs are available to be assigned. Only when all of the needed resources can be assigned or available can a process be allowed to start running. Now, in the early days, when the operating systems were all batch systems, generally it was not too difficult for programmers to identify all the resources that the program would need. But as the systems became interactive, it became really infeasible to require users to identify all the resources that they're going to need in advance. Well, for one thing, with the interactive users tend to be relatively unsophisticated and not always aware of exactly what resources the program is going to need. Interactive systems generally try to improve the use of their resources by using dynamic resource sharing, running the program until they need the resource and then requesting it. But dynamic resource sharing increases the chance of a deadlock occurring. When a deadlock does occur, the only way to recover is to make one of the processes release a resource so that the other process can proceed. Of course, rolling back, releasing a resource might very well result in a loss of information. Now, there are lots and lots of systems that can almost always tolerate that kind of a data loss. But there are others, real-time systems, where that kind of a data loss could prove disastrous. Life support systems in hospitals, aircraft guidance systems can't afford to lose information at all. They have to avoid the kind of deadlock that requires the loss of system. Now, a deadlock situation can arise only if all of the following conditions hold. Mutual exclusion. At least one of the resources must be held in a non-shareable mode. Otherwise, the processes wouldn't be prevented from just going ahead and using the resource. A process holding at least one resource and requesting additional resources that are held by other processes. And a resource that could only be released only voluntarily by the process holding it. Finally, circular wait. Each process must be waiting for a resource that's being held by another resource, which in turn is held by another resource, which is eventually, with a need, a holding for a resource in one of the earlier processes in the sequence. These four conditions are the Kaufman conditions from their first description by Edward Kaufman in 1971. Mutual exclusion, hold and wait, no preemption, and circular wait. Most operating systems do not prevent deadlocks, not totally. When a deadlock occurs, different operating systems respond in different ways. Most of them try to prevent one or eliminate one of the four Kaufman conditions. Most commonly, they attack the circular wait condition. Starvation is a name given to indefinite postponement of a process because it requires resources to continue, but the resources never get allowed, not because they cannot become available, but because other higher priority processes are continually utilizing them. This can be avoided typically by a process called aging. That is, every once in a while, increase the priority of processes that have been waiting. This way, when a process has been denied access to a resource often enough, eventually it gets its priority raised up to where it is going to get access to the resources.